I
Oh, that's
apologize
fine.
for that
That's fine. Okay.
sound, but yeah. So the conjugacy classes of the equilateral triangle you asked us to find a geometric
Hmm.
perspective. What I think is happening is any even number of not parity, sorry, any even number of reflections finally end up being some sort of rotation. So when we are doing a conjugacy class when we are trying to find the conjugate to of any rotation operators, then what happens is, if even if we take the even if we take conjugate it with respect to a reflection, since there are two numbers of reflections, like if I consider a
Hmm.
inverse, then since there are a inverse is equal to a, since there are even number of reflections involved, so it ends up being rotation. So uh, yeah, so any even number of reflections, if it has an even number of reflections, then it's essentially becomes a rotation. uh, is that what you meant by
You're
a
close
geometric
in the
perspective?
sense that you are halfway there. But you have managed to establish that if you are only dealing with operations like rotations and reflections, it's very easy to see that only rotations can be conjugate to rotations and only reflections can be conjugate to reflections. One of the easiest ways of seeing that, it's actually much easier than your statement right now, although it's essentially the same thing, is that if you look at the matrices, the determinant of your matrix for a particular operation cannot change under conjugation, right? Because you're going to go to a similar matrix. Okay? So it's impossible for a rotation to be conjugate with a reflection or a
Yes.
reflection to be conjugate with a rotation. That is correct. Okay? However, this does not tell you. Okay, let me just see one thing. There is something called a whiteboard here. If I've never seen this. This is a new thing. I've not seen this before. Let's see whether I can use it at all. It's saying something like creating jam. Oops. Some people, okay, share. Oh, wow, it seems to be a bit complicated. So let's share with 7 people. Okay, turn link sharing on. No, share with 7 people. Okay, let's see. And then there's a pop-up window which gets blocked. So this apparently is a Jamboard. Okay, fine, but can we do something on the Jamboard? Okay, since my pen tablet can write on the Jamboard. So I'm not sure whether this is at all more useful than what we had before. Can you all see a white screen now? Or you have to accept something perhaps?
Yeah, it
You
opens up in a different tab.
can see a white screen which says open on a Jamboard on a corner or something. You can see a cursor moving on that. Yes or no? If you can't, let me know. Okay, Anuran Pal joined. So you have to keep on joining to the jam, I guess. Can all of you do that?
Sir, I have to install an app, so it will take
Okay,
time.
then let's ditch this. It's not really that important. Okay, let's ditch this for the time being. Sorry for that. I didn't know that this is available at all. Let's just go to our standard mode of usage, which seems to have worked pretty well till now. Let me just turn on. Yeah, this is, I've turned on the Zoom now, but I need to present.
So the reflections have a determinant of
Yeah, reflections
-1,
have a determinant of -1.
and the rotations are
Rotations are
+1.
+1. So it's, as I said, it's impossible for a reflection to be conjugate to a rotation and vice versa. Okay, but that's correct. But that's only part of the whole story. Okay, when I say it's a part of the whole story, it's because let's just take a look at something slightly more complicated now, at least a group with a slightly larger number of operations. In our group, the one which we talked about, the one which had E, A, B, C, D, F, the classes came out sort of straightforward. E was in a class of its own. All the reflections were in a class of their own. The other two non-trivial rotations were in a class of their own. Okay. Now you can actually explicitly find out what kind of conjugacy would say which element in the group G will lead G to F. That is, which of the G group elements really give you G, D, G inverse is F. That's pretty straightforward to find out. Now, as you can see very well here, rotations are not conjugate with reflections, so they don't belong to the same class. Reflections don't belong to the same class as rotations. But it's also true that not all rotations belong to the same class, right? There are three rotations in this particular group, which are D, F, and also this is the one which we tend to miss, E, right? E is also a rotation. It's a rotation to 0 degrees. These three are not in the same class, right? Two of them are. E is in a class of by its own, which is always the case in any group. But just to see this in a bit more detail, or see that this is a rather simple group where you don't get to see all the possibilities. But suppose you were talking of the symmetry group of a square. This is also pretty straightforward. Now you have, say, the symmetries like this. Reflection in this plane, reflection in this plane. You also have reflection. Now my drawing is going to be pretty bad here, but you have reflections along the diagonal. I wanted to draw a diagonal there. Maybe I will just make use of this. Yeah, this is the in one diagonal. This is reflection in the other diagonal. So there are 4 reflections, right? 2 along mid planes, 2 along diagonals. There are 4 rotations, right? 0 degree, identity, 90, 180, and 270, right? So basically we can give them names again. Let's call this, call these A, B, C, and D, let's say. And then we have, so now you have E, A, B, C, D, and then you have F, G, and H. So F is, say, 90 degree counterclockwise, this is 180 degree, this is 270 degree. You're all with me so far? These are the group elements. These are the 8 group elements for the symmetry operations of a square.
Sir, your board is not visible.
My board is not visible. Am I not presenting? No, I'm not, apparently. My presentation got cut off.
Sir, I installed the Jamboard application, so we can start. If you can try that if you want.
Well, let's try this for the timing. Let's not go into something new today. We will do some practice before trying that. In any case, I will have to use essentially the same. I see I get the same functionalities there. So unless something, I seem to be losing my connection quite regularly. I don't see why. Because my connection otherwise is pretty stable. Okay. Let's see. Can you see it now? My attempt at drawing a square.
Yes, sir, we can see it.
And now you have 4, well, just to repeat, there are 4 reflection symmetries. One is, 2 of them are just the medial lines, that is, you join 2 midpoints of opposite sides, and 2 of them are along the diagonals. And you have 4 rotations actually, identity, which is 0 degrees. And then you have F, G, and H, 90 degree, 180 degree, 270 degree rotations. Okay. Now, if you figure out the conjugacy classes of this one, you will find that the conjugacy class structure goes like this. E is in a class of its own, which is the case in any group, not a surprise. It so happens that G, the 180 degree rotation, is also in a class of its own. F and H together are in a class, and AB is in a class, CD is in another class. So, as I was saying, you are right in saying rotations and reflections cannot stay in the same class. But it's not enough to just be a rotation or just be a reflection to be in the same class. See, here A and B are in the same class, C and D are in the same class, but they are distinct classes. There is no way you can conjugate A to get C or B to get D. Similarly, among the rotations, we already knew that the identity will be in its own class, always. That's the case in all groups. But we also see here that G, the 180-degree rotation, is in its own class. And the other two rotations, they share a class, F and H. Can anybody see the connection here? Now with this slightly more larger group, you may be able to sort of guess which elements go into the same class, which elements don't. You already know which elements don't. Rotations, reflections, never in the same class. But as you can see here, AB and CD are not in the same class. AB is in a class on its own, CD is in a class on their own. CD are in a class of their own. So, any guesses? What makes them go in the same class or not go in the same class? Let's start with the rotations. Can you guess why F and H are in the same class whereas G isn't?
Order of the
Sir, does it have to do with?
Go ahead, one by one.
Yeah, does it have to do with the index of the group element? Like how many times the group element has to multiply with itself to go to the identity, like become
Well,
the
actually, it's
identity?
simpler than that. You can translate it to index, I guess, by a convoluted series of arguments, but this is much simpler. Anybody remember what the rotation matrices looked like in 3 dimensions?
so the presentation stopped.
Oh. So maybe the whiteboard, I'm not sure, there is actually stopping because I'm losing connection somehow today. So let me do one thing. Let me try does everybody have the whiteboard, Jam? Yeah? Let's try the whiteboard. Let's see. So are you logging in through a phone or something? That's why you need an app, right? So on the browser, I'm just getting a browser board.
Yes, I'm
2 whiteboards right now. Let's try one of them. Is everybody with me here? Can everybody see this white screen now? If any one of you can't, please speak up. And I hope I'm still in here.
Yes, sir.
Something is going wrong today. Usually it's not that bad. Okay, so going back to what I was talking about, let's try drawing it again. So I was trying to draw a square and making a mess of it. I just got a bit of a hang of it before in Zurnal, but this still should sort of give you the impression. We said this is A and this is B. That is, reflection along these lines are A and B. Reflection along this diagonal is C, along this other diagonal is D, and we have this E, A, B, C, and D. 5 operations.
Sir, I can't see anything on the Jamboard.
You can't see anything on the Jamboard. Are you
Neither,
sure you are
sir.
looking at the same Jamboard?
I can't.
Can anybody else see this?
I also can't see anything on the Jamboard.
I
Sir,
can
I
see
saw
this.
two
You have to choose the other Jamboard. I mean,
there are two Jamboards.
I can see this.
Which other Jamboard?
When you open it, there are two options for the Jamboard. When you first open the link, there are two Jamboards.
Open the second link.
Yeah, I've opened the second link. A second link that Sir sent in the chat box, right?
Open the first link actually, sir. The
Yeah,
Jamboards are
open the
open.
first link.
Well, actually, I lost connection. Can people see this now? I'm back connected, I guess.
Ah, yes, sir.
Hmm?
Yes, sir.
I can
Yes.
see 4 of you joined here. I think that's it, right? You can see the square. My rather pathetic attempt at drawing a square with diagonals, you have to figure out whether these lines, okay, there should be ways of drawing nice images here, but let's not try to experiment too much right now. So what we talked about is this. The classes turned out to be E, AB, CD, and how does one, I guess, yeah, but let's finish this here. FH and G. So 5 classes for this particular 8-element group. My question to you is, can you see why? That is, what is the connection between which AB has, which CD doesn't, which FH has, which G doesn't? And for that, you tried answering this using order, and that's fine, but let me just remind you that suppose a rotation matrix about the z-axis to an angle theta. What does it look like? And you have cos, cos, minus sine, sine, right? Okay. Now this is of course for a specific matrix through a rotation about the z-axis. But if you were to rotate about any other axis n hat, do you know how to get that? Say, if you know the rotation matrix about some axis n hat, do you know how to go from Rn hat to Rn prime hat? Where two rotations by the same angle through different axes. Do you know how you can change one matrix over to another matrix like this? Yeah, am I still with you? So the question which I asked right now is, can you figure out Rn prime theta, where n prime is some axis, if you know Rn theta, where n is some other axis? So that's a general question. Of course, we will specialize to Rz theta, z being n hat soon, z hat being n hat soon. But in general, how do you go from a rotation about one axis to a rotation about another? You should know this. I'm definitely taught this in the 3rd year. And apart from that, this has been used, I guess, several times in several courses.
Change of basis coordinates with respect to n prime and then rotating.
Now that's possible, but there's an easier geometrical way of seeing this. All you really need to do is find one rotation which will rotate n prime into n. Some rotation curly r, whose job is to change n prime to n. Now there are infinitely many such rotations, but any one of them will do. And if you do that, if you have such a rotation, what you can always do is first do curly r, which will change n prime to n, then rotate about n through an angle theta, and then do curly r inverse. That is, go take n prime, n back to n prime. Now I will let you worry about why this actually gives a rotation about n prime through an angle theta. It's pretty easy to figure out, but do think about this. This is a very easy way of going from one axis to another. Okay? Now what this actually tells you is it tells you something about the trace of the rotation matrix about any rotation matrix about any axis through an angle theta. Can anybody tell me what that has to be? In fact, okay, I should actually display the whole screen here. To see the whole Jamboard, you should be able to say immediately. What is the trace of Rn hat theta, where n hat is any arbitrary axis whatsoever?
2 cos theta plus
Yeah, it has to be 1 plus 2 cos theta. Why? Because ultimately you can find a rotation which takes you from Z .
Sir, I can't hear you.
Even I can't.
Oh, okay. Monica, did you message him?
Messaging him now.
Okay, I hope I am back.
Yes, sir.
And so, did you hear about the 2 cos theta argument? That is, basically what I said was, if two rotations are about different angles, two different angles, then they definitely cannot belong to the same class. Is that okay?
Yes.
So let me just try to find a better network. I don't have a better network. Okay. I will just be off and back. Am I still here or have I lost connection?
You are here, sir.
Okay. I hope this will improve things, but anyway, let's see. So the basic idea is that the 180-degree angle rotation here is the only rotation with 180-degree as its angle. It can't be in a class with anything else. F and H are both 90-degree rotations. They can be in a class together. Now, both 90-degree because one is 90, another is 270, but it's really 270 is really minus 90, which has the same cosine, by the way, right? 270-degree has the same cosine as 90 degrees. So theta and minus theta both work, or you can say basically it's about 90-degree about the opposite axis. However, just having the same angle is not enough. You must have some symmetry operation which will change this axis, one axis into another. Okay. Similarly, A and B, for reflections, the case argument doesn't really tell you much more. Because as you can always easily figure out, all reflections have the same trace. So basically, what happens is you need to have an operation which will take you from one reflection plane to another. So notice that there is a symmetry operation in this group which takes you from A to B, right? If you rotate through 90 degrees, A becomes B. This is why A and B are in the same class. A and C are not in the same class because to go from A to C you have to rotate through 45 degrees, and a 45-degree rotation is not in your class. Is this clear? There is no 45-degree rotation in this group. Sorry, not in your class. I was wrong. It shouldn't be not in your class. I should have said not in your group. There is no 45-degree rotation here. So no symmetry operation takes you from A to C, which essentially is the geometric interpretation of these classes. Rotations can be in the same class only if they're the same angle, but that's not enough. You also need an operation which will change one of the axes of rotations to the other. In this case, there's a 180-degree rotation which will achieve that job. Reflections will belong to the same class if and only if there's a symmetry operation which actually changes one of the planes of rotation into the other. Why that is the case, I will leave you to worry about. This is pretty straightforward now. Okay, so if you are done with, if you are sort of convinced about that, if only temporarily, let's move on to the next part. That is, let's go back to our representation theory. Can we do that now? Or do you have any other questions?
Yeah.
Okay, last.
Sir, sir, this this Jamboard thing, will this come in the YouTube videos that you will upload?
Okay, it will, in the sense that I'm recording the thing, right? I'm hoping that the entire thing is recorded. I don't know. It may not. So, well, we're doing this for the first time, so I have no idea. So there's a possibility that the Jamboard will not come in the YouTube, or maybe it will come as a separate file. I'm pretty sure it will come as a separate file which you can load. I'm not sure whether the recording also records the Jamboard along with it. It should, ideally, but I don't know. Okay, so let's just see. In any case, I'm not really liking the Jamboard all that much. So unless, and it seems not to have improved my connection scenario anyway. So what do you say? Will we ditch this and go back to the standard tablet mode and presentation?
Yes, sir.
Yes.
Well, let's do that. Because the next part has a lot of maths, and it's important to have that actually recorded. But I don't expect people to follow all the math immediately anyway. Okay, so I hope you can see my better attempt at drawing the square here. Can you see that?
Yes, sir.
Okay, that means at least
Yes.
it's working now. So let's go on. Let's standard. Okay, so just to remind you, we had ended up last day with this rather important relationship, which in fact many books actually call the great orthogonality theorem, because this is the one which is actually, okay, this is the great orthogonality theorem actually. D alpha G, D beta, G inverse, sum over all group elements, work out to be mod G by D alpha, case of Z, delta alpha beta times the identity. So this was a result that we had, and we showed that this immediately led us to a conclusion, that is, if you took the elements for this and also exploited the fact that you could choose Z arbitrarily, you end up with this result. So some books will call this the great orthogonality theorem. Anyway, it's just a matter of nomenclature, but this previous line is basically where everything gets started, and we will need it again later on. And just to remind you, what we did from here was we put I equal to I prime, j equal to j prime, summed over all I and j, and ended up with this result: sum over g belonging to capital G, pi alpha g, pi beta g inverse, where these are the characters, worked out to mod g delta alpha beta, or using the fact that all representations of finite groups are equivalent to unitary representations, we ended up with this result: chi alpha g, chi beta g star is delta alpha beta, which was this idealized orthogonality relationship. This is of course sum over all group elements. You can also rewrite this as sum over all classes and this led us to the conclusion ultimately that if we form a vector like this, with as many components as the number of classes, and we did this for each one of the inequivalent irreps we are using, then these vectors will end up being orthogonal, and that immediately gives us this result that the number of inequivalent irreps has to be less than or equal to the number of classes. Okay, and then we said we will be able to show that the number of inequivalent irreps is equal to the number of classes by showing that these vectors actually are not only orthogonal to each other, they also form a complete set in the set of class functions. That is, if you define, okay, what are class functions? Class functions are simply functions which map classes in a group to numbers, right? That means every element of a given class has to give you the same value. If you take the set of all class functions, they obviously form a vector space whose dimension is the number of classes, and you can show that these vectors, the ones which we have written down, one for each irrep, they span the entire set of class functions. We will show that, and that will complete the proof that this is not less than equal to, this is actually equal to. But before we go there, let us quickly figure out many of the results which I alluded to in the last class, did not really prove, but they're pretty straightforward to prove even without the completeness thing. Okay, and they are going to be the most useful relations that you actually use here. So first of all, how do you reduce a reducible representation? In other words, what we are trying to do is, given a representation, we want to find out, can it be reduced into irreps, and if so, which of the irreps of a group actually figure in that reduction, and how many times do they figure? Okay? So that is what we are trying to do here. Is the question clear? In other words, let me remind you that a reducible representation will end up having matrices which look like this. A irrep block here, maybe several times, another irrep block on the diagonal, and so on. But it's not true that the representation will always look like this. All I am saying is you should be able to find a similarity transformation, a single similarity transformation which changes each and every one of these matrices, DGs for all the Gs, into the same block diagonal structure like this. Okay? And you should realize that this is a pretty difficult task, basically because it's not even diagonalizing a given single matrix. If it's a large matrix, is a pretty tough ask in general. Here you're not doing that. Here you are trying to block diagonalize all the matrices corresponding to all the group elements using the same symmetry transformation, and that may be very difficult to find out unless you have help. And the help is provided essentially by this orthogonality theorem here. Okay? So we will later talk about exactly how to do the reduction as well. There are many applications where you don't even need to know what the exact reduction is or what the similarity transformation is. All you need to know that it can be done and what kind of irreps are present in the reduction. If you know that, that's enough for many purposes. For some purposes, you need to explicitly know the reduction. Okay? That's a bit more advanced. We are going to cover that later. For the time being, let us just ask ourselves, given this particular possibility of a reduction, can we figure out from what we have learned so far how many times a given irrep occurs in a reducible representation? And the answer is pretty straightforward. First of all, realize that you can write the DG symbolically as this. So what does this notation mean? It essentially means that you can write the matrix DG not necessarily immediately in this form, but at least it's similar to a matrix where you have M alpha, you have D alpha, the irreps belonging to the inequivalent representations. The alpha is inequivalent irrep M alpha times. Okay, so maybe in a particular reducible representation, a particular irrep occurs twice, another occurs 3 times, another occurs 5 times. So this will really be 2 times D for the first one, 3 times D for the second one, 5 times D for the third one, and so on. Okay. Now, the only problem with this representation is that this is only symbolic, in the sense that until and unless you find out the symmetrizing transformation, find out the similar transformation, you don't really have a block diagonal form like the one I drew above. However, the important and great thing about characters is that character, after all, is a trace, and trace does not change with the similarity transformation. So this result will always be true as a strict sum. Is this okay with everybody? Please let me know whether you have understood this, because this is of course the critical part in the argument. That if a irrep occurs M alpha times in the representation, no matter how hidden that is because of mixing up of the bases, when you take a look at the character will definitely contribute M alpha times. Is this okay? Can I go on?
Yes, sir.
Okay, and just to remind you, we had this relationship, right? The orthogonality of characters. Yeah. Go ahead.
Sir, just a clarification. This M alpha is actually D alpha being added M alpha times, right? D alpha
is there in the representation or M alpha times, right? So basically what you did was you formed a direct sum representation, perhaps by just putting the D alpha, the alpha representation M alpha times, and you mix them all, and then perhaps you even mix them all together by changing the basis, so that you can no longer see the block diagonal form. But even when you do this, you are changing your basis, so your matrix, all the matrices get mixed up and loses their block diagonal form, but the characters don't change because the character is invariant under a similarity transformation. So when you put them in a block diagonal form, it's easy to see that the character would be m alpha chi alpha g summed over, and that has to stay the same no matter which basis you're choosing. So that's the beauty of working with the characters. Even if you are choosing a messed up basis, it doesn't really make a difference. The characters stay the same. Okay. Now finding out m alpha from here is actually pretty straightforward. All you do, and well, notice that this is really like a dot product, right? You take one element for every g, multiply them together after conjugating one of, okay, the star is in the wrong place, of course. You can't have a conjugate of g, right? Or a complex conjugate of g. What you have is chi beta g's conjugate. Okay? So you take the chi alpha g, chi g's, take the corresponding chi beta g's, conjugate them, multiply them together, add up. That's really what the inner product is like. And the inner product here is delta alpha beta, apart from this mod g factor, which means that they are orthogonal. And this immediately gives us this result, that if you did this, so chi g, you already, suppose you have a representation in your hands. So if you have a representation, you can easily figure out the characters. So you know the characters, let's say, and you just want to find out m alpha. So how do you do that? You just figure this out. What is this going to be? This sum in here is just this sum, except that since I'm using alpha here, not as a dummy index, I have to use beta or some other label for this index of summation. But then all you have to do is interchange the sum over the representations and sum over the group elements, and do the sum over the group first. And if you sum this over the group, you're simply going to get mod g delta alpha beta, which implies that, okay, this is equal to m alpha times mod g. So how do you find out the number of times a particular representation irrep occurs in a representation? You just take the character of the representation chi for every element, multiply it by the complex conjugate of the character for that particular irrep for the corresponding element, sum over the entire group, and just divide this by 1 by mod g. That's it. So just to remind you, this is very similar to something we have done since class 12. How do you find the x component of a vector? You dot it with the vector along the x direction. So how do you find out the alpha component of this vector chi g, which is m alpha? You just dot it with chi alpha star g, or dot it with chi alpha g. The dotting involves the star anyway. It is okay with everybody. And of course, I can simplify this, or at least shorten the work a bit, by not summing over all the group elements, but just summing over the classes. Simply by taking into account the fact that since character is a class function, both for the reducible representation and the irreducible representation, you will end up with the same contribution from every element which belongs to the same class. So you can just sum up over the classes, remembering to weight the contribution of every class by multiplying by the number of group elements in that class. So this of course becomes a smaller calculation, because typically a group has smaller number of classes than group elements. Okay. So this is the basic formula which allows you to find out from the characters how many times a particular irrep occurs in a reducible representation. Are you with me so far? All of you?
Yes.
Okay. Now let's move on to the next question, which could have even been an earlier been the first question to be asked here, although the answer actually depends on this result that we have shown right now. That is, we should really have first checked whether my representation that I have is reducible or irreducible to begin with. Okay, reduce C. Ability. I want to figure out, given a representation or given just the characters of that representation, for most of what I'm going to do today, and even for most of what we are going to do with finite groups anyway, the characters will be enough. Not all of it, but for most of it. Okay? So suppose you're given the characters of a particular representation. The first question which you should ask, even before asking how many times irreps occur in that particular representation, is simply, is the representation at all reducible or is it irreducible? Okay? If it is reducible, only then will you go and ask how many times different things occur. Just hold on, I need to answer the door. Okay. Anyway, it seems that I don't have to. Somebody else is doing that for me. Amazon. Okay. So now notice. Now, you just start with the result that we had a while ago. Chi alpha C, chi beta P conjugate. This is our central result actually. The orthogonality relation for characters. Now, if you put alpha equal to beta here, that is, if you are talking of a single rep, this immediately tells you that sum over all classes NC chi alpha C mod square has to be equal to G. Mod G, sorry. Is that okay with everybody?
Yes, sir.
And now it turns out that this, so if the representation is irreducible, it will definitely obey this. And it turns out that the converse is also true. If for any representation, sum over all classes NC chi C mod square. Remember, I am no longer putting the alpha label here. I do not know whether this is irrep or not at this stage. Is mod G, or this of course is the same, remember, as sum over all the group elements, or just chi G mod square, right? If this happens, then the representation is irreducible. So to figure out whether a group is representation is reducible or not, all you have to do is check this sum. You take all the characters, take their mod square, add them up over all the group elements. Or if you're just dealing with characters for classes, which you will usually do because that's less work, you will just take the mod square of the characters for the classes, multiply them by the number of elements in each class, and add up. If that turns out to be the number of elements in the group, the result of the sum, then your representation is irreducible. Okay, let's go in for the proof of this last part. And the proof is really simple. Notice that for any representation, you have this, right?
So it has to be a multiple of a number of group elements.
Yeah, but if it's exactly equal to the number of group elements, then which one? You mean this sum, right?
Yeah, for any representation, if you're given any representation, then if the if summation c and c chi c mod square is uh, an integer multiple of the number
Mod
of
G.
total number of group
That's
elements, mod
always
g,
true.
yeah, then
Yeah,
it will be
that's always true. And that will be clear if you don't know that already from the proof that we are going to do right now. However, the point is if it is actually equal to 1, it says equal to the number of group elements, then the representation, then and only then is the representation irreducible. For a reducible representation, it's going to be more than mod G. Okay? And that will be clear, clear from this calculation very soon, because if we take a look at this and then just form this. What is this going to be? This is going to be sum over all the class elements, MC times sorry, I'm pushing this too close to the edge, so let's. M's are of course integers, so they don't conjugate. Their conjugates are the same as themselves, right? I've just written chi c twice here, chi c and chi c star. I've just taken care that the summation index is different for the two cases so that we don't get confused. But then it's easy to see that this becomes m alpha, m beta, and the sum over the class, which if you do first, simply gives you mod G delta alpha beta, right? So this is going to give you mod G times sum over alpha m alpha square. Since m alphas are integers, of course, if you square the integers and add them together, you're definitely going to get an integer. So your first statement was right, that if you do it for any representation, reducible or irreducible, you are going to get a multiple of mod G. The factor is going to be this sum. Sum over alpha of m alpha square. But now, is mod G. What does this tell you about this sum? This is equal to 1. And the only way this can be equal to 1 is
if it's an EDEP.
Yeah, because if only one of the m alphas is 1 and the others are 0, there's no other way, right? If you add a lot of squares together, there are no ways of getting negative contributions which will cancel other positive contributions. So the only way this can happen
Sir, why are m alpha only integers? Why can't they be reals?
you are actually putting, remember what you're doing, you're saying you're putting together smaller representations to build up bigger representations, right?
Yes.
That's what reducibility means. So how many times do you use a smaller representation? That's exactly what m alpha are.
Oh, okay.
If you're putting using a representation once or twice, you cannot use it 1.75 times, right?
Yes, sir.
Okay, so m alphas have to be integers. They have to be positive integers, or to be more precise, non-negative integers, right? Can be 0, but cannot be negative. Cannot even be cannot definitely be fraction. So this implies that m alpha equals 1 for one of the alphas and 0 for the rest. Hence proven, hence irreducible. Hence our representation has to be an irrep. Is it okay with everybody? Clear?
Sir, would you please show the definition of n of C again? Just once.
Oh, n of C is just simply number of elements, number of group elements in a class.
Okay, okay.
So remember, the sum is over actually all the group elements, right? But every one of the group elements in a class contribute the same result. So instead of summing up over all the group elements, you can just sum up over the classes, remembering to weight the contribution of every class by the number of group elements that are there in the class. That way, you end up working less because you add up over the smaller number of terms, but you don't miss any term. That's important. Is this okay?
Yes, sir.
Okay, so what we have done, we have been able to find out a machine by which you can actually find out the number of times an irrep occurs in a reducible representation. We have also found out a criterion for irreducibility, that a given representation, you can easily just look at the characters and do a simple straightforward calculation. The calculation is almost trivial. Just take the mod squares of the characters, add them all together over every group element, or just weight them by NC and add up over classes. And if that result is mod G, it's an irrep. If it's not mod G, it has to be more than. Not only has it to be more, as pointed out a while ago, it has to be an integer multiple of mod G. If it turns out that you do a lot of long calculation and at the end this comes out to be not an integer multiple of mod G, there's one sure shot way of knowing that you have made a mistake. There's a sort of check that your calculation is going in the right direction. Okay? But anyway, assuming that your calculation is right, you have to get an integer multiple of mod G. If it happens to be mod G equals just equal to mod G, you have an irrep in your hands. Now let's go back to a result which we have alluded to several times. Let's look at the regular representation, which we have already stated is reducible. Stated, not proven. But for the regular representation, we know this for sure. So in the regular representation, this red here just tells you that we are in the regular representation here. The characters are very straightforward. What are the characters? If G is not the identity, the character has to be 0. If G is equal to the identity, the character has to be mod G, right? Everybody remembers that about the regular representation?
Yes, sir.
Okay, good. So having said that, now let's first check, is this reducible, yes or no? So our criterion of reducibility, you just take the characters, mod square them, add them together. What do you get?
Mod G square.
And this is greater than mod G, unless, of course, you have the very trivial case that the group is the singleton group with only the identity, right? Okay. So this implies okay, done. Yes or no?
Yes.
Yeah.
Well, this one is easy, and of course you can see that this sum is actually a multiple of mod G. It's mod G times mod G, which of course is an integer multiple of mod G. Okay, now the really interesting question: if this is reducible, what is its reduction? How many times does each irrep occur? Remember, a given irrep may or may not even occur in a particular reducible representation, right? So the great thing about the regular representation is, as we stated without proof so far, then it contains every one of the irreps. How do you do that? How do you know that? You just find out M alpha. And how do you find out M alpha? You just calculate this. For any representation, you just do this. But if you're doing this for the regular representation, asking how many times does the irrep alpha occur in the regular representation, you have to do this. And then what happens? In this sum, all terms drop out, right? Because chi regular G is 0 for almost every one of the terms except for one, which is the identity, right? So you're summing up over all the group elements. Only one of the group elements contribute in this sum because this factor vanishes for every one of the others. For the one for which it doesn't matter, you can mod G here, right? Because that's the character of the regular representation for the identity. And you have to multiply it by the character of the representation alpha for the identity, which is how much? What is the character of the identity for any irrep? Either for any representation, by the way. The identity is always represented by what?
Identity.
The identity matrix. The identity operation is represented by the identity matrix. And what is the trace of the identity matrix?
Dimension of the representation.
Okay, great. So it has to be T alpha here. So the result that we have been quoting so far. Notice the D alpha is not 0 for any of the alphas, which means that all the representations that you have, all the irreps that you have figure in the regular representation. Okay? And because they all figure in the regular representation, not only do they all figure, they also figure exactly as many times as the dimensionality. So one-dimensional representation occurs once, a three-dimensional representation occurs thrice, and so on. Clear? So this is something we have already stated in the last class, but this is a simple proof of that. Once you have the orthogonality law for the characters, this follows rather trivial. And this immediately tells us that you must have this. I hope everybody remembers where that came from. So we already did this exercise in the last class with the equilateral triangle symmetry group. We said that there are three classes, so three D alphas, and the squares must add up to the number of elements in the group, which is 6. And we saw that for S3, or the symmetry group of the equilateral triangle, you ended up with 1, 1, 2 as the only possibilities for D alphas, which means you must have two one-dimensional representations, one two-dimensional representation for S3 in terms of irreps. Okay? Now what about let's try to see whether we can do the same thing for our square. For the square, we had this. These are the classes. Five classes, right? 1, 2, 3, 4, 5. A G is sitting alone. 5 classes. 5. That means 5 distinct irreps. Although that's again a result which I have not proven yet. All I have proven so far is that you can have at most 5 classes, but at least let's assume that to be true for the time being until we complete the proof. So there are 5 distinct irreps whose dimensions are all of course integers, positive integers, whose squares add up to 8. So can you see how that's possible? One thing is this immediately rules out three-dimensional representations, right? You cannot have a 3D rep, 3D or 4D or 5D irreps, right? The maximum size of an irrep for this particular group, the symmetry group of a square, has to be 2. Is it okay? And what are the sizes now?
4 one-dimensional and one
Yeah, the only possibility is 1, 1, 1, 1, 4. 1, 1, 1, 1, 2. Right? Because that's the only bunch of 5 non-negative integers whose squares add up to, or 5 positive integers really. Here, you can't have a 0 dimension because you're talking of irreps only. This is the only combination of 5 positive integers whose squares add up to 8. So the symmetry group of a square must have 5 distinct irreps, 4 of which are one-dimensional, 1 is two-dimensional. So there's quite a lot of information you can get immediately with some very simple look at the characters. Okay? You're not even looking at the characters here because you don't even know what the characters are so far. We will figure that out soon. We will figure out the character table of these groups by using simple, straightforward arguments based on the orthogonality relation and so on. But my point is you can figure out a lot of information about these irreps just by looking at the basic results that we have. Okay? So now let's go in for the final proof of the day. This is going to be a rather lengthy proof, which is that of completeness. Okay? So what you want to prove is this. So what does this mean? It means that if you have a class function, which of course means you have one value for every class of a group. So it's essentially like a vector with as many components as the number of classes. Such a class function can always be written down as a linear combination of the vectors that you have formed by taking chi-cs. Or if you want to make calculation slightly easier, vector with components root over nc by mod g times chi-c. The root over nc by mod g just makes the vectors, these vectors orthonormal rather than just orthogonal. So we need a proof of this, and this proof is a bit complicated. It's a bit lengthy. I'm not even sure whether the proof I'm going to give you right now is the most optimal one. I have not had time to think about it very thoroughly. But it does look like there are several steps in the proof which might be reduced. I don't know. This may be a good exercise. Try to make the proof that I'm going to give you simpler. That is, try to cut down on the steps a bit. But the proof that I'm going to give you essentially works like this. We start with, where else? Start with the create orthogonality relationship theorem. D alpha G But what we do is we specialize that. We specialize in the sense that rather than worry about two different irreps here, let's stick to one single irrep. So instead of using alpha and beta, we are using alpha is the same as beta. And then, of course, what you will have is mod g by d alpha trace of z times the identity. The only difference between the general case and this one is you had a delta alpha beta in the general case. That, of course, is 1 here. Okay. Now, let me ask you once again, so what can you say about this matrix Z here? That is, for what matrix Z is this valid? Yes?
Any choice of Z, right?
Well, almost. Not any choice of Z, but any d alpha by d alpha matrix Z, right? It has to be the right dimension for the matrix multiplication to be possible. Otherwise, other than that, any choice. Remember, when we were talking about the general case, it was d alpha by d beta dimensional. Here is d alpha by d alpha dimensional square matrix. So any Z will do. Completely arbitrary Z. So what we do is we choose Z to be of this form. Is this okay with everybody? I can always choose such a z, right? Z, where z prime is now some arbitrary, completely arbitrary square matrix of dimension d alpha. Okay, and G1 is some element. So d alpha G1 is a representative matrix for some particular group element, a fixed group element. Is this clear? So what I do is just take this and plug it back in this equation. And what do we get? I get G belonging to capital G. I get d alpha G1, d alpha G inverse. So I get d alpha G1, G inverse, using the fact that these are representations. So homomorphisms anyway. So mod G by d alpha, trace of Z prime, d alpha G1 times identity. So what do we do next? What we do next is simply we use find out the ijth element. This is a matrix relation, right? So I find the ijth element of this matrix. So this becomes so this should really be familiar. We have done this already once, but we are doing this for a slightly specific choice of the Z. Mod G by d alpha, and then what do you get? You get trace of Z prime d alpha G1 delta Ij, right? Now, can anybody tell me what the next step should be? I mean, what is the obvious choice that you do in the next case? And moreover, how many different equations have you written here actually?
D alpha square equations.
D alpha square distinct equations, right? D alpha square independent equations, because you have D alpha square independent choices for Z prime KL. And then what we will do is we will just choose a specific Z prime KL which will make my life easier, and the choice in fact should be sort of obvious. We have already done this before. The only difference is we did this before for Z. We have now written Z as Z prime D alpha G1, and we are doing this for Z prime. That is, we are saying, okay, Z prime could be any matrix, any square matrix of this size. Let us just choose a square matrix for which only the I primeth and row and J primeth column has a 1, every other element is a 0. And notice that if we do this, we are not losing any information, simply because if you find out the information which is there for each one of these d alpha square choices of Z prime KL, that is, just choose I prime J prime to be whichever row and whichever column you want, you essentially have this, exactly the same information here as in your original equation. But if you make this precise choice, then your calculation becomes a lot simpler, right? What does your calculation now tell you? With this particular choice, what happens? What happens to the left hand side? The sum over KL of course simplifies. You have d alpha G, then I, what do I put here? I prime, right? Yes, sum over K is trivial now, I can just do that. Similarly, I get d alpha G1 G inverse the L becomes J prime after you do the summation. So that's what happens to the left hand side. What happens to the right hand side? Of course, you have mod G by d alpha delta ij, sorry, delta ij, which was already there, but now you need this trace. So let me just work out for you what this trace is. Remember, this is the trace that you're going to put in for this particular z prime. So then, of course, you sum over k and l of z prime k l d alpha g1 lk, right? Is that okay with everybody? That's just z prime d alpha kth element summed over all k, right? But what is this going to be? This sum with our specific choice of z prime kl, of course. I have a specific choice of z prime kl. I've chosen a particular matrix z prime. For that, what will this trace turn out to be? It will turn out to be d alpha g1s. Okay, then what? Which element of d alpha j1?
J prime I prime.
Exactly, j prime I prime, because L will be replaced by j prime and k will be replaced by I prime when you do the sum, when you do this sum here. So what you have, going back to our original equation, is this is d alpha g1 okay, just to remind you, if you had already seen a special case of this relation earlier, because if you choose G1 to be identity, the left hand side simply becomes the immediate consequence that we had from the GOT, and on the right hand side you get d alpha identity is J prime I prime element, which is of course delta I prime J prime. So one of the first equations we started with today, that is started with when we talked about representations. Let's go back a bit. Further, even further. Just a reminder, this relationship. Do you see the connection between this one and what we wrote down a while ago? This one is G and G inverse. What we wrote down as G and a G1 here. G1, G inverse here. And there, instead of this thing, what you have is D alpha G1's J prime I prime element. So as you can see, this is actually a general, you might call this result that we wrote down right now a general case, a generalization of this result, because this is a special case. Okay. However, I will just urge you to think about it a bit. After all, how did we derive this? The result we derived came out of this relation, right? The GOT. And this relation, the relation without that we wrote down a while ago. If I am allowed to scroll back all the way, or just pick it out from here. This relation, the one in black, is actually exactly equivalent to the GOT, right? Because it has no. By the way, this doesn't have less information than this one. This has exactly the same amount of information. The two are essentially equivalent statements. So frankly, saying that our last relation is a generalization is a bit of a stretch. It's actually not a generalization. It's exactly equivalent to that one, but looks different and is useful in a different way. Are you with me so far?
Yes, sir.
Okay, so we have a new relation. The question is, so what? Well, one thing you can immediately do is that you can bring in characters here. You have a group element on the right hand side. How do you change that to a character? This d alpha g1 j prime I prime, you have a relation for that, right? How do you change that to a character relation? How do you get a character out of this? Come on, how do
Take
you
I equal to I prime and j prime equal to j.
make what? Not too much. You just make j prime equal to I prime. That's it, and sum over I prime.
Yeah. Ha ha ha.
Right? But if you do that, if you put, you have to do it on the left hand side as well. And here, if you put j prime equal to I prime and sum over I prime, what are you going to get on the right hand side? Sorry, on the left hand side. It is putting I prime equal to j prime and sum up. Sum over I prime. What are you going to get on the left hand side?
D alpha G G1 G inverse of
Exactly, because that's just matrix multiplication. Not that, the ijth element of that. Right? And on the left hand side, you're going to get mod g by d alpha delta ij and chi alpha g1. Is it okay? Are you with me so far?
Yes.
We have got this result that if you sum over all the group elements, this quantity, the ijth element of that, you are going to end up with mod g by d alpha I alpha g1 to delta ij. Now let us just do one more thing. Let's exploit the delta ij by multiplying both sides by d alpha g2 ji. Why ji should be obvious. So let's do this. Let's start with what I have already. This is what I already have. I just rewritten what I had. But then I multiply both sides by d alpha g2 jith element. So I do it for both of this, and on this side, of course, I have delta ij, d alpha g2's jith element. But G2 is any other group element, right? G1 is some arbitrary fixed group element, G2 is another arbitrary fixed group element. Could even be the same as G1 for all I care, but could be different as well. Again, what would you do with this? If you really had something like this, what's the most obvious thing you can do to this? If you see something like d alpha ij and another d alpha ji, you should be crying out for one further step, which is
summation of over j.
Summation over j, definitely, right? But because we love characters, sum up over both j and I, on both sides, of course. So what does if you do that, summation over j, of course, because that gives you a matrix multiplication, obvious matrix multiplication rule. However, that will just give you an iith element of a matrix. But once you got to the iith element of a matrix, it's obvious that you would love to sum up over I to get the character, right? So what does this side give you? Tell me what this is going to give you.
A character of G, G1, G inverse G2.
A character in the alpha array of G, G1, G inverse G2. Good. And on this side, what do you get? And what is this going to be?
Chi alpha G2.
Yeah.
Exactly, chi alpha G2. So we are nearly there, but then we are going to do something which looks a bit crazy. What we are going to do, or actually it doesn't really look crazy in a hindsight, but what we are going to do here is we are just going to multiply post size by d alpha by mod g. So you get chi alpha G1, chi alpha G2 on the right, which I have just switched to the left. That of course is G alpha G1, G inverse G2 on the right. Of course, this is not crazy. This is just rewriting the previous line. But then what we do is something like this. We sum up over all the representation, all the adepts you have. Remember, when I say all the adepts, I mean all the inequivalent adepts, always. So this was for a particular adept so far. We have chosen only one alpha. But there are several adepts, and we form the same contribution for each one of them and add them all together. So what we are going to get? Okay, you had a sum over G. Yeah, I forgot to write that. But now you also have a sum over alpha. Maybe I will just squeeze in some space here. But can anybody see why I did this? In particular, do you recognize what this is? Yes?
Regular representation?
Well, you're right. If you weight characters by the dimensionality of the rep and add them together, what you end up with is simply a character in the regular representation corresponding to this element. Is everybody with me so far? Because that's what the regular representation is, right? Every irrep occurs d alpha times. So the character in the regular representation for a particular group element has to be the character of that group element in the irrep times d alpha summed up over all alpha. We have just used that. But why have we used that? We have used that because the regular representation has a very straightforward and simple choice for the characters, right? And before we just exploit that, what we will do is we'll just slightly switch things. And let's see how many of you can tell me immediately what we have done here. Okay, everybody has followed this step? What have we done here? What did we do to get to
The
this?
fact that it's unitary.
No, we did not use the fact that it is unitary because representations don't have to be. But you're close. Close, but not exactly correct. You did use the unitary somewhere, but representations don't have to be unitary.
So that should be G2 inverse, right?
Which
In the
one?
LHS, in
No.
the left hand side. No.
No, 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 no.
Okay.
Actually, it is not G2 inverse on the LHS. But you're close in the sense that what I did was put in G2 inverse in place of G2 throughout. Okay?
Okay.
And then use the fact that every representation is equivalent to a unitary representation, and hence chi alpha G2 inverse is chi alpha G2's conjugate. Okay? Right? Why did you do that? Because basically the conjugation is an inherent part of the inner product that we are using. So it's best to put it in this form. Now comes the final answer. Okay, almost the final answer. Can you tell me what is this going to be? Remember, we know everything about the regular representation. We know all its characters. So that's what makes it so easy. So what's your conclusion?
Okay, before. Very.
Yeah. Go ahead.
This on the RHS G1 G inverse into G2 inverse is very similar to how you derived the multiplication, how you related the multiplication table with the representation. That any G, the representation of any G can be expressed as G I G J inverse.
In the regular, you mean in the regular representation, right?
Yes.
Okay,
Yes.
but not really that. The point is, what I'm trying to make is this: you know that there's only one element in the only one group element which gives you a non-zero result in the regular representation, which is only one element in the group has a non-zero character in the regular representation, which is identity, right? Is it okay?
Yes.
So that means that this is important. Whether G2 and G1 belongs to different classes, this quantity G1, G inverse, G2 inverse will never be identity for any G, right? That this being equal to identity actually tells you that there is a conjugation which changes G1 to G2. If this is equal to identity, this really is the same as, this equal to identity is the same as G2 is G1, G inverse, which means G2 belongs to the same class as G1. Okay, so if G1 and G2 belong to different classes, then no matter which of the group elements you use, in fact you have to sum up over all the group elements. So for every one of the group elements, this quantity is not going to, this element is not going to be the identity. And because only the identity has a non-zero character, you're going to end up with 0 from every term, which is you're going to get a 0. Okay, clear? I don't want this to be a proof by intimidation, so I want to know whether this is really clear.
Yes, sir.
Okay, so what can you what can this tell you about the characters? In particular, let's go over to classes here. Instead of summing up over, okay, sorry. Summing up over all alpha. So chi alpha c simply means take a class, pick an element from there. Okay, chi alpha c prime means pick another class, take a element from there, and just find the character. What can you say about this? This has to be
Delta CC.
close, but not quite. It has to be 0 when c is not equal to c prime, right? But when c is equal to c prime, that is, if g1 and g2 belong to the same class, then this sum, what will this be?
Mod G.
No, it will be mod g for each one of the small g's for which g2 is g, g1, g inverse. Okay, let me point out one thing. It is not correct to say that there is only one small g when g1 is similar to g2 means what? There exists a g in the group G such that g2 is g, g1, g inverse. There exists one, but that doesn't mean only one. There may be more than one, right? And for each one of those elements for which g2 is g, g1, g inverse, this term is going to give you mod g. Okay? So this lambda c here, of course the mod g is going to cancel with the mod g here. The mod g which comes from this character is going to cancel with the mod g here. But you are going to essentially be left with simply the number of elements G in the group which actually connect G2 to G1. Do you get my point? Yes?
Yes, sir.
Now I will ask you to think about this a bit. It's pretty straightforward, but a little bit of thought will actually tell you. By the way, we are already done with our proof of completeness, because once you have this result, that this is proportional to delta cc prime, showing completeness is almost trivial from here. You have done this several times for linear vector spaces. I'm pretty sure you should be able to do it. This is basically the same thing as this result. Sum of all projectors is identity. That's basically what you're doing, except that there's a slight hitch here in the sense that this constant is not necessarily 1, but doesn't really matter. Even without that, the completeness is already done. But I will urge you to complete the proof. But anyway, I will also urge you to figure out that the number that you have here is actually this. That is the number of group elements which actually carry you from a particular element of a class to another element of the same class happens to be actually exactly equal to the order of the group divided by the number of elements in the class.
Is this because the? Is this because? So I'm just taking an example of S3. Then if I see the class ABC, then ABC, the conjugate class of ABC, then for each element, I get A twice, B twice, and C twice.
Yeah, but you get A twice, B twice, C twice because there are two elements which carry A to, well, actually two elements which carry A to A, but there are also two elements which carry A to B. There are exactly two elements which carry A to C. Why is that the case? In fact, these elements are basically either this, that you have to figure out, either which two elements are doing the job. Because, for example, if you say A to A, of course, it's not DNF. For A to A, one of the elements is obviously the identity. Right?
Yes.
Okay, so I will urge you to think about this exactly. You're right. You're on the right track. And your answer is right for S3. but I am asking you to think of this in general. For a general group, why is this the case? Which also tells you one more thing. The number of elements in a class has to be a divisor of the number of the order of the group, right? Now that's, by the way, not obvious because a class is not a subgroup. So Lagrange's theorem doesn't work here. Okay, a class is obviously not a subgroup because there's only one class which has the identity. All the other classes don't have the identity. So they do not form subgroups. But they share with the subgroups this property that their size has to divide the size of the group. Again, I will urge you to think about why that is the case. Simple group theory, and perhaps it's best to take a look at two simple examples, the equilateral triangle one and the square one. If you just figure out the specifics for all of them, you should be able to find out the answer. Okay, as to why. Okay, but actually if you just look at this really tells you which, remember, is nothing but the alpha, or the cth element of our class vector, the orthonormalized class vector. Is it okay? You might say you did not really have an NC prime. You had two NCs. Square root and you just had an NC. But because of the delta CC prime, it doesn't really matter. Right? If C and C prime are different anyway, remember there's no sum over C here. The sum is all this square root NC prime is a term outside the sum. The sum would have given you a 0 anyway if C were different from C prime. So this particular result actually sort of exactly mimics orthogonality relationships for vectors. It is the orthogonality relationship for vectors and the completeness, in fact both. So if you have a bunch of say, should I really actually explain this? I don't think I should. All you need to do from here is to show that any class function can be written down or you can just throw in the root over NC by mod G just to make later calculations easier. And you can find out F alpha C from here. You can find out F alpha C just by using the orthogonality relation. But notice, if you use the orthogonal, okay, but by the way, are you following this here? All I'm saying is, suppose I have a class function, that is, I have a function which takes a value for every one of the classes in a group. Then I'm claiming that I can always write FC as F alpha C, chi alpha C. Well, root over NC by G, okay, you can even just drop that part. It's not really that important. Let's forget about this. After all, you could just as well incorporate the root over NC by G as part of these coefficients. So if you could write that, what will F alpha C be? Yes? Come on, this is straightforward. How would you find the coefficient of chi alpha C from a sum? Yeah, sorry, you broke up.
Multiply f of c by chi alpha star of c and then sum over alpha.
Exactly, chi alpha C star, sum over all the group elements, and divide by mod G, or sum over all the classes. That could also work. but then throw in an NC here, right? Now, there's one catch with this. This works only if FC can be written down in this form. Okay? That is only if FC can be expressed in terms of all the chi alpha C's. Just linearly combining them gives you all the FCs. Gives you the FCs. We have not proven that yet, or we are claiming that we have proven that because we have the completeness relation written down just a while ago. But we are trying to see why this is really the completeness relation. But before we go there, can you tell me one thing? We have already used this, right? We have already used this today several times. But how could we use that without proving the completeness relation first? Yes?
The orthogonality itself gives us.
No, the orthogonality gives you. Look, the orthogonality tells you that if f of c is this sum, then f alpha c is this. Okay, that's important. You have to assume first that f of c is a sum of this form. Only then f alpha c will give you this. Only then orthogonality will give you this. If it's impossible to write fc as a linear combination of chi alpha c's, then there's no way this result will follow. So that's a subtle point, but that's an important mathematical point. You did that when you said orthogonality gives you this. Orthogonality tells you that if you start with a sum like this, and if fc really is this, then f alpha c will be this. Okay. But when we are trying to claim completeness of the chi alphas, that's exactly what we are claiming. We are claiming that you can write down any class function as a linear combination of the chi alpha c's. Now, why? That is something we are going to prove now, that you can do that. And we will prove that simply using this result that we have just now proven, that this is true. Okay? However, the question I'm asking you now is this. We have already used this method when we found out m alpha, right? The number of times an irrep occurs in a representation. And all these other results, like how many times with the regular representation and so on. So are these, were those proofs incomplete, or at least were those proofs done before we had all the machinery to prove them? In other words, were they logically incorrect at that stage? Or was it logically correct to just use the orthogonality theorem there? Do you understand what my question is here? That's important.
I mean, in those cases, we knew that it was some linear combination of the irreps.
Exactly. In that case, those cases, because we knew that a representation is built out of irreps, okay, and that's what a reducible representation is, right? It has to be reducible. It has to be possible for you to break it down into irreps. And if you can break it down into irreps, then the corresponding characters have to be of the form m alpha c chi alpha c, right? M alpha chi alpha c. If there was not even m alpha c chi alpha c, the m alphas were, in fact, even here the notation is wrong. There is no c here, right? There's just f alpha. You multiply the chi alpha with some constants, and just you are claiming that you get an fc. So there, of course, by the very nature of characters, you already knew that the character of a reducible representation had to be a linear combination of characters of the irreps. So because you knew that already, using the orthogonality theorem was fine. We are now claiming that this is going to work for arbitrary class functions. Give me any function which depends on the class, I should be able to write it like this. Now, why is that true? Well, the check is simple. If you assume, let's assume you can, then you get this as f alpha. Then what do? Then you plug this f alpha back here. And what do you get? You get sum over alpha. So this is your f alpha which you have plugged in. And then you have a chi alpha c. What's your next step? The next step is obviously doing the alpha sum first. Then what happens? These are independent of alpha, they come out of the sum. And you just sum up over this, over all alpha. And what is that? So question is, if I plug this f alpha back in this sum, do I get back fc? If I do, then I'm fine. If I don't, then I'm in trouble. But I do. That is to say, if I start by assuming that I can write f of c as a linear combination of all the chi alpha c's, then find out the coefficients of the chi alpha c's from the based on that assumption using orthogonality, then take these coefficients, plug them back in the sum. I do get f alpha fc back. If I do, then my original assumption was correct. If I don't, then the original assumption was wrong. Do you get my point? Yes? No? Maybe? Okay, let me just go back to a very simple class 10 example or a class 12 example. Let's say I have an ordinary vector which is 3i plus 4j plus 5k. Okay, this is your vector A. And somebody has gone and said that I and j form a complete set. They are of course orthogonal, no problem. They are also orthogonal to k. But you are now claiming that I and j form a complete set. That's it. Nothing else is there. Okay. Now, because I know I and j are orthogonal, then if I can easily find that the coefficients of component of I will be just a dot I. The coefficient of j will simply be a dot j. So by assuming that I and j are complete, what we are saying is A is C1 I plus C2 j. That's what we are claiming now. And then C1 has to be A dot I and C2 has to be A dot j. That's trivial. But now what happens? If I take this C1 and C2 which I got from the orthogonality relation, put it back in my sum C1 I plus C2 j, do I get back A? Yes or no?
No.
No.
You get 3i plus 4j, which is not the same as A. What that means is, because you're not getting back A by following this procedure, that shows that your original assumption that A can be written as C1i plus C2j is wrong. Clear?
Yes.
So I and j did not form a complete set despite being orthogonal. Okay? The same thing works here. So far what we had was with these vectors we formed with chi alpha c's, they were orthogonal to each other. So we already knew they were linearly independent and hence they could not exceed the number of classes in number. Okay? Now what we do is we are claiming that okay, let's look at a class function. Now a class function essentially is a vector with as many components as there are classes, right? When you say FC, there's one number for every class. So basically you can write that as a vector, column vector, row vector, whatever you want. One element for every class. Okay? So it's a NC, not NC, okay, NC is wrong because NC is the number of elements in a class. So hash C, dimensional vector. Now you're claiming that you can write f of C, this vector. Now, so I've just written down one component of this, but this is really a single component of the vector. The vector really is this fc1, fc2, and so on. I unfortunately don't have a good notation for the number of classes, final, and so this is the vector we have. We are claiming that this vector can be written down as a sum over all alpha of, sorry, f alpha times that's the real claim that we are making. We are then showing that, okay, because I know that these vectors which involve the irreps are all orthogonal, I can use the orthogonality relation to find out what f alpha is from here. But now when I take the f alpha and plug it back, question is, do I get back my original full vector fc1, fc2, fc hash c? Or in other words, if I look at a particular component, do I get back f of c? In the previous case, if I looked at component number 1, I did get back 3. Component number 2, I did get back 4. But if I looked at component number 3, I got 0. There was no component in the result. But the actual vector did have 5. So here what happens is that for every component this matches up, which means my claim that I can write down the vector, this vector, as a linear combination of all these irrep character vectors is actually correct. So the irrep character vectors do form not only an orthogonal set but also a complete set. And because they form a complete set, complete linearly independent set, there must be a basis which completes our proof that the number of irreps is exactly equal to the number of classes. So this proof was a bit lengthy in the sense that we started with started with a standard orthogonality relation. Then we said this is true for every z. So let me just quickly recap the proof for you. We said this works for every z, so it also works for a special form of z, which is essentially z prime d alpha g1. Notice that because d alpha g1 is invertible, I can actually write any z in this form, right? So this is not really something very specialized. And then we just plug this in, take the ijth element of that, then play the same trick as before of choosing a very special z prime with only one element equal to 1, every other element 0, which ultimately gave rise to this simple result, which we then further exploited by using the fact that there is a delta ij here and there's an ij element here, by multiplying by d2 alpha g2 of ji and summing up over j and i, changing the whole thing to a character on both sides, got a relationship between characters. Now so far we were talking about single irrep alpha. Then we said, okay, let's sum up over all the irreps after multiplying by d alpha, and that gave us this regular representation version, and that give us this nice result that this sum will actually vanish unless j1 and j2 belong to the same class, which essentially is all you really need to finish the completeness. The rest of it is just window dressing. The completeness result is proven the moment you do this. So I will urge you to try to think of it in any simpler way of arriving at this result. Maybe some of these steps could be cut down a bit. I don't know. But this looks, the proof is okay. There's nothing wrong with the proof. All I'm saying is I'm not very satisfied with the length of this proof. It may be possible to simplify this a bit further. Okay. So all the basics of the orthogonality theorem and representation theory are done now. What we have to do next is we have to actually apply them to specific groups and try to figure out results. In particular, one situation which will be very important is we will have to talk about how to find out how to reduce direct product representations. There are many situations where you have systems made out of different pieces and each piece transform according to some representation of a symmetry group. Then the overall system will transform like a direct product of those representations. It so turns out that direct product representations are almost always reducible, even if the original representations were irreducible. And figuring out how many times a given array occurs in a direct product representation is a very important occupation because it tells you a lot about physical results. So we are going to do that. We are going to go towards doing that starting from the next class. Okay? So I will stop today. If there are any questions, do you have any questions before we end up today? Or we have already gone way too long? By the way, if I overextend my time and you are getting bored or you have something better to do, please stop me. Okay, because I lose sense of time, especially when I do something like this. But that's me being nice to you, so you better take that offer while it's still there. Anyway, today I'm going to stop anyway, so let's just stop the recording.